Hello students, in this video lecture number 1, we are going to study about the capacitors from the beginning. What is a capacitor? First of all, see the figure. In this diagram, I have shown this is a real capacitor which is fitted on the motherboard of electronic circuits. See, the capacitor has two terminals. Actually, one of them is longer, representing the positive terminal, and smaller one represents negative terminal. This is a electrolyte type of capacitor. Right side figures, these are showing ceramic capacitors. As you can see, these materials are ceramics. Inside the ceramics, we have two conducting plates, and in between them there is a ceramic material which act like a dielectric. Dielectric, you know, it is a non-conducting material, is called as a dielectric. Anyways, but in our syllabus, we have to study three types of capacitors: parallel plate capacitors, spherical capacitor, and cylindrical capacitor. And in this lecture, we'll discuss what is the definition of capacitors, means what are capacitors, what is the definition of capacitance, and what is a parallel plate capacitor. And we'll do the derivation for capacitance of a parallel plate capacitor, and the remaining derivations, spherical and cylindrical, we'll do in the next lecture. So let us start. So what is a capacitor? A capacitor is an electrical device that is used to store electric charge and electrical energy. This is the basic definition of capacitor. Okay, so a capacitor consists of two conductors placed very close to each other with a very small gap. The gap may be filled by a non-conducting dielectric medium, like this. Suppose that this is a conductor. Any random shape, okay? It could be any shape. Although we study parallel plate capacitor, but we can have two conductors of any shape. Let us say this is the conductor A and this is the conductor B, and this is the gap between them. The gap between them could be, let's say right now we take it as air only, because you know air is also a dielectric medium. Air is non-conducting medium. So this set of a pair of two conductors which are placed very close to each other makes a capacitor. Why do we call it capacitor? Because it has the capacity to store electric charge. Let's see how does it store electric charge. Let us connect two terminals of wire to these two conductors and connect it with a battery. So here is a battery connected to the two terminals of the conductors. Let us say the voltage of this battery is V, potential difference, and this battery has a positive terminal and negative terminal. The positive terminal is supposed to be at high potential, and the negative terminal is at low potential, and V is the potential difference between them, higher potential minus lower potential. Let me say that higher potential is V1 and lower potential is V2. Then this battery potential difference V will be V1 minus V2. Okay. Now, after we connect this battery to these two conductors, what will happen to these conductors? Let's see. So in electrostatics, we have a theorem or a statement which says that, so in electrostatics we have studied that when two conductors are connected to each other, their potentials become equal. So when the high potential terminal, positive terminal of the battery is connected with the conductor A, the conductor A should have become same potential as that of the positive terminal. So the A will be at high potential. The conductor A will be at high potential. Its potential becomes V1. As you can see, V1 is the potential of the positive terminal. Similarly, the conductor B is connected to the negative terminal of the battery, which is at low potential V2. So therefore, the conductor B will now have low potential, the value V2, right? So now we can see that conductor A has acquired a potential V1 and conductor B has acquired a potential V2. So now there is a potential difference between them, A and B. A is at higher potential, B is at lower potential. So now we can say that in a capacitor there are two conductors, and one conductor will be at higher potential, other will be at lower potential. Let's see what happens next. So what happens that this battery will supply electric charge. The positive terminal of the battery will supply positive charge plus Q, and at the same time the negative terminal of the battery will supply charge minus Q, same amount, and these charges will go into the conductors. Like this. Now after these charges enter into the conductor, first point you already know that charges always reside on the outer surface of the conductors, not inside. So these charges given by the battery, they will remain only on the outer surfaces. So I will show here the charge is on the outer surface. No charge can reside inside the conductor, inside the volume of conductor, not possible. So the charges are on the surface only. Now you may ask that why not the charge spread on the entire surface, whole outer surface and inner surface, I mean to say entire surface of the conductor. Why these charges are going inside? So answer is due to attraction between positive and negative charge. You know that positive charges attract the negative charges, both attract each other. So due to their mutual attraction, all the charges will go on the inner surface of the capacitor. So please note, in a capacitor, the charges stay only on the inner side of the conductors due to mutual attraction. So positive and negative charge attract each other and they are on the inner side. If you separate these conductors to very large distance from each other, then the charges would spread all over the surface. Entire surface will be covered. But when they are brought near to each other, then due to mutual attraction, these two charges will come on the inner side of the conductors. So what happens now, after the charges are developed on the conductors, an electric field would be generated. Let's read here. Now these charges will produce an electric field whose direction will be from the positive charge towards the negative charge. We know that whenever there are charges, an electric field would be developed. So we'll draw electric field lines from the positive charge to the negative charge. Also, while drawing these electric field lines, we should take care that the electric field lines must be starting perpendicularly from the surface of the positive conductor and they should end perpendicularly on the negative charge conductor. Let's read here the concept. Also, the electric field lines always start perpendicular to the surface of the conductor and also end perpendicularly to the surface of conductor. So from the positive charge they start perpendicular and on the negative charge they end perpendicular. So in this manner we can see that this electric field is actually a non-uniform electric field. These electric field lines are not parallel because the shape of the conductor is not uniform, that's why. So this is the electric field E generated between the two conductors. Also note that electric field lines cannot exist inside the conductor because you know that the inside of the conductor is always having zero electric field. There cannot be any electric field present inside the conductor. So inside the conductor electric field is zero, so no electric field lines are drawn inside the conductor, but from positive to negative charge in this region we have our non-zero electric field. So that's all the working and functioning of a capacitor. You see how the capacitor stores the electric charge. In fact, now if you disconnect the battery, if you cut the wires and remove the battery, then also these charges will remain on the conductors. Why? Due to mutual attraction between them. They will not go anywhere. They are not lost. If you disconnect the battery, then also in between the two conductors an electric field would be present and the charges will retain on the surfaces. Now we can define capacitance. What is capacitance? Capacitance is the ability or capacity of a capacitor to store electric charge when a potential difference is applied to it. As we saw in the above diagram, that when we connect a capacitor to a battery, Then the battery supplies charge and the charge gets stored in the capacitor. What I mean to say by stored is that if you disconnect the battery, if you cut all the wires, then also the charges will remain inside the capacitor. So that is why we can say capacitor stores the charge. So how much amount of charge it can store? That ability is called as the capacitance. But also another point to be noted is that from experiments it was found that the amount of charge stored in the capacitor is directly proportional to the potential difference or the voltage applied to it. So we write down that the charge which is stored inside the capacitor is directly proportional to the voltage applied to it. Now in the diagram above, how much charge is stored? You see plus Q charge given by the positive terminal. So the charge which is stored on the positive terminal or positive conductor is plus Q, and the charge stored on the negative conductor is minus Q. So in total, we can say the total charge stored on the capacitor is actually 0, Q and minus Q. But when we say charge on the capacitor, we actually talking about the charge stored on the higher potential conductor or the positive charge stored in the capacitor. So we'll say that this capacitor stores charge Q. Although the total charge is 0, but we will say that the charge on the capacitor is Q. So the charge means the charge on the positive terminal. So we'll say the charge Q is directly proportional to the voltage or the potential difference applied to the capacitor. Now if you write down here the sign of equality, then we should put a constant of proportionality here. Let that be constant of proportionality is C, and this constant of proportionality C is called as the capacitance. Capacitance. Therefore, finally we can say that the capacitance of a capacitor is now defined as capacitance C is equal to Q by V. That means Q means the amount of charge stored, divided by the voltage applied. This is the definition of capacitance. So we should note down this as the formula. C is equal to Q by V. Now, as we have now defined a new term, let us write down what is the SI unit of measurement of capacitance. SI unit of capacitance. So the SI unit of capacitance will be equal to the unit of charge divided by unit of voltage. The unit of SI unit of charge divided by the SI unit of voltage. So SI unit of charge is coulomb and the SI unit of voltage is volts. And this ratio of coulomb by volt is also known as farad. F-A-R-A-D, farad. Symbol is capital F. So we can say that the SI unit of capacitance is farad. Generally, the farad is a very large unit. So in practical sense, we will be using smaller units of farad. For example, microfarad, which is 10 power minus 6, or nanofarad, 10 power minus 9, or picofarad, 10 to power minus 12 farad, okay, etc. Smaller units will be used here. Let us also discuss that what is the dimensions of capacitance. Dimensions which are written in terms of MLT. Capacitance C is defined as Q by V, charge upon voltage. So voltage is voltage is potential difference, and the potential difference is actually work done per unit charge. So we have Q square by W, Now let the Q square be as it is. W, work done. Work done can be written as force into displacement, and the charge can be written as current into time, current I into T whole square. Now we know the dimensions of these things, okay? Current dimension of current is written as A. Dimension of time is T. So we get here A square T square divided by. Dimension of force is mL T power minus 2. Because force is mass into acceleration. So mass is m acceleration L T power minus 2. And D means distance. So that is dimension is length L. So finally we can say m to the power minus 1. This L and L multiply become L square. In the numerator that becomes L power minus 2. And T power minus 2 goes up and becomes T power 4. And A to the power 2. A means ampere, or sometimes instead of ampere we can also just write down I as the dimension for current. So this is the dimension for capacitance. Now it is the time to discuss about the parallel plate capacitor. So here is a parallel plate capacitor. It consists of these two conductors A and B, which are now in the shape of thin parallel plates. So the battery will supply charge plus Q charge from the positive terminal and minus Q charge from the negative terminal. As I already explained that the charges will remain only on the inner faces of the plates due to the mutual attraction between the positive and negative charges. The positive and negative charge will be on the inner surface only, and also there will be an electric field developed here. So now this time we can say electric field lines will be parallel to each other, because as I said earlier, the electric field line should start perpendicularly from one plate, one conductor, and land perpendicularly on the other conductor. So because these two plates are parallel, so if you draw a line which starts perpendicular from the one plate and ends perpendicular to the other plate, it will be like a straight line only, okay? And also the distance between the two plates is very, very small. So because the distance between the two plates is very, very small, this D distance is very small, so therefore in the very small gap the lines has to be almost parallel to each other. Also the plate area of the plates is supposed to be A. Plate area A. Also note here that on the outer surface there are zero charge. The capacitor has zero charge on the outer surface. Here also zero charge. As I said, charges will be only present on the inner surface. And this is our electric field E. So the first task is to find out what is the electric field developed here due to the charges. The charges are plus Q and minus Q. So here we have plate charge plus Q, and this plate the charge is minus Q. Due to this positive and negative charges plus Q and minus Q, how much amount of electric field is going to get developed here? Let's find out. So to understand the formation of electric field between the plates, let us first assume that the plates are far away. So, and also we assume that charge is only on the one side only. This is the charge Q. You know that the electric field produced by a plane sheet of charge is given by the formula sigma by 2 epsilon naught, where sigma is the charge per unit area, Q by A. So Q by 2A epsilon naught. So this positive plate will develop an electric field whose direction would be from the positive charge towards the negative charge, and this electric field will have a value E is equal to sigma by 2 epsilon naught, or you can also say Q by 2A epsilon naught. Secondly, this negative charge develops electric field which is directed inwards into the negative charges, because you know that electric field lines they terminate or end into the negative charge. So the direction of electric field would be towards the negative charge. and this magnitude of electric field again given by the same formula, sigma by 2 epsilon naught, and because the magnitude of charge also the same, so q by 2a epsilon naught is the electric field. So both the positive charge and negative charge are developing their individual fields. But when you make the plates closer to each other, then the electric fields due to each plate will get added up. This is the electric field due to the positive plate, and this electric field due to negative plate. Both of them will get added up together. So electric field due to the positive plate is sigma by 2 epsilon naught, and electric field due to the negative plate is also sigma by 2 epsilon naught. So we can say the total electric field in between the plates will be the electric field due to the positive plate and plus electric field due to the negative plate. As the direction of both electric fields are same only, so we have to add both of them. So we will get sigma by 2 epsilon naught plus sigma by 2 epsilon naught. Please note no minus sign here because the magnitude of electric fields we are adding here. So the total electric field will become sigma by epsilon naught. Hence, we can conclude now that electric field in between the plates of a capacitor is equal to sigma by epsilon naught. So let's write down here, electric field in between the plates of capacitor is sigma by epsilon naught, which is also equal to q by a epsilon naught in between the plates of capacitor. Now we should discuss about the relationship between the electric field and the potential difference. We have already found the electric field here, and now we will find out what is the relationship with the potential difference over here. First of all, we should note that V is the potential difference of the battery, but as we discussed earlier here, that the potential difference of the battery is V. So V1 is the potential of the positive terminal and V2 is the potential of the negative terminal, and after connection same potential V1 and V2 are the potentials of the two conductors. So the potential difference of the battery V1 minus V2 is same as the potential difference between the two conductors. So we can say now that the potential difference between the plates of the capacitor is same as the potential difference of the battery. So in the diagram we can show that the potential difference between the plates of the capacitor is equal to V, same as that of battery. How is this potential difference V related to the electric field E and the distance between the plates? That is what we want to find out. So let us write down the formula. From electrostatics, we know that potential difference between 2 points V2 minus V1 is equal to minus of integration E dot dr from the point 1 to 2. Now here, let's understand what is the meaning of point 1 and 2. So let us say if this is the positive plate and this is the negative plate, positive and negative plate, okay. So what we do that, we will construct a line, an imaginary line, okay, and the direction of that imaginary line will be from the point 1 up to the point 2. So 1 is the initial point, 2 is the final point, and we are going to travel along this path, okay, and in this integral dr is a small displacement along this path. This is dr, okay, small displacement, and the direction of electric field is also in the same direction because the direction of electric field from positive to negative plate in a capacitor. So first of all, on the right side, this dot product E dot dr will be written as E into dr into cos, A dot B is AB cos theta. So E dot dr will become E dr into cos 0 degrees because the angle between E vector and the dr vector is 0. And cos 0 is equal to 1. So this will be equal to E into dr. Let us now substitute the value of electric field as we calculated above. we found that electric field in between the plates of a capacitor is sigma by epsilon naught. So write here sigma by epsilon naught. You may also write sigma as Q by A, charge upon area of the plate. So Q by A epsilon naught into dr. Now, to perform this integration, let us take the constant things outside. So charge Q is constant on the plate, area of the plate A is also constant, and epsilon naught also constant. So everything gone outside except dr. And the limit of integration is 1 to 2, from 1 to 2. Now, what is the integration of integration dr? Well, let's see. So dr is a small amount of length on this path 1 to 2. Okay, straight line path 1 to 2. So integration means the summation of the dr length. So this entire path can be broken down into several small dr vectors, and the total sum of all the dr vectors will be equal to the length of this line 1 to 2, and the length of that line is nothing but the distance between the plates. So therefore the integration of dr is nothing but the total path length, which is d, distance of between the two. Now on the left hand side, what is this V2 minus V1? V2 belongs to the negative plate. So V2 is the potential of the negative plate, minus V1 is the potential of the, see, this is the point number 1 on the positive plate. So V1 is the potential of the positive plate. Now there is a minus sign on the right hand side. Let us write this in the opposite manner. So V positive minus V negative, that becomes Q by A epsilon naught multiplied by D. And now this difference, this potential difference, potential of the positive plate minus potential of negative plate, if you see the diagram here, then this side you see positive terminal, plate A has the potential V plus V positive, and plate B has the potential V minus V negative. So positive potential minus negative potential is nothing but the potential difference V between the plates. So we can now write it as V. So this is potential difference V. V is equal to Q by A epsilon naught into D. Right. But we were about to find out the relationship between electric field and the potential difference. Now you see electric field is sigma by epsilon naught, which is same as Q by A epsilon naught also. Right. Sigma by epsilon naught is same as Q by A epsilon naught. So can we say that from here we have also found out the result like this, V is equal to E into D. So this is the relationship between the potential difference and electric field in a parallel plate capacitor. V is equal to E into D. Well, after we have found out this relationship between potential difference and the electric field, now we can now find out the capacitance. As if you go up and see the derivation above what we did, the formula here, capacitance is defined as Q by V, charge upon potential difference. So now it's time to find out the capacitance of a parallel plate capacitor. Okay, so the capacitance of a parallel plate capacitor can now be written as, so definition of capacitance is a charge upon voltage, potential difference. Right. So if you look at this formula derived above, potential difference can be written as E multiplied by D. So capacitance of a parallel plate capacitor can be written as C is equal to Q by V. This is the definition of capacitance, charge upon potential difference. Now if you look here, what is the potential difference that we derived above? Substitute here. Potential difference is Q by, sorry, not, there is no 2 here, Q by A epsilon naught, Q by A epsilon naught into D. Now the charge Q gets cancelled and A epsilon naught comes here in the numerator divided by D. Therefore students, we have derived the formula for capacitance of parallel plate capacitor, which is written as epsilon naught A by D. Now, if you look at this formula, we find something, a very special thing can be concluded after deriving this formula, that the capacitance of a parallel plate capacitor does not depend on the charge stored in it, because the charge got cancelled here during the derivation. It depends only on three things. One is epsilon naught, which is permittivity of the medium. A is the area of the plates and D is the distance between the two plates. So capacitance depends only on the geometrical factors. Let us write down. So the capacitance of a capacitor neither depends on the charge stored in it nor the voltage applied. You may think that capacitance is defined as the ratio charge upon voltage. So capacitance must depend on the charge and also on the voltage. But that is not true actually. Capacitance depends only on the three factors, which is the medium between the plates. Medium means the epsilon naught for the vacuum. Or if you put any other medium, then we will write down epsilon. Area of the plates, and thirdly distance between the plates. So capacitance depends only on the geometrical factors and the medium between the plates. So this is the end of this lecture. Please write your comments and let me know. So the next video I am going to discuss about the capacitance of the spherical shaped capacitor and cylindrical capacitor. Thank you.